we've been talking about this differential equation here, which I've suggested can serve as a model for understanding the dynamics of a protein that can switch between an active and inactive state. And the dynamical variable that we're studying, x, is the proportion of active proteins, x star, over the total amount of the protein, regardless of its activation. So in this video, we're going to pick apart this dynamical system a little bit more. Now, remember that this system is a homogeneous differential equation. Sorry, not homogeneous, autonomous differential equation. And there's actually a very important theory about autonomous differential equations, equations that don't have any explicit time dependence on this side of the equation. And that theory goes a little something like this. As t approaches infinity in an autonomous linear differential equation, then x, or whatever dynamical variable you have, basically has two choices. X can either grow or decay to infinity, or x can approach a constant value, which we denote as x steady state. And this theorem here I'm not going to prove, but I will include a reference to this theorem in the description of this video. And if you're interested to see why this theorem holds, you can study it more, and it's actually pretty simple. It shouldn't take you too long. Just read the chapter that I post, and this basic theorem should make sense to you. Now, what I said in the previous video was that x has to be within the interval 0 to 1 for all time, assuming that we pick the initial condition to be a somewhat reasonable, that is, within this interval to begin with. So knowing this condition tells us that this first option, that x will grow or decay to positive or negative infinity, is impossible, because we know that x always has to be between 0 and 1. So when alpha and beta are constant, and that's an important condition, because if alpha and beta are constantly changing, then you wouldn't expect x to approach a constant steady state value. But if alpha and beta are constant, x will approach a constant, which we denote as x steady state. And this basically falls out of elementary dynamical systems theory and the study of ordinary differential equations. So now what I want to do is derive the steady state for x. So we want to find xs. So how do we find xss? Well, we know that in the steady state, the definition of the steady state is that dx dt equals 0. So when x equals the steady state, it stays there forever. And I don't know if this terminology is sort of, you can think about this as something growing and approaching a steady state value. So this purple dashed line is xss in this case. And if this is your dynamical variable, it's sort of approaching the steady state, and when it reaches, it sort of asymptotically approaches steady state, never quite reaches it, but if it ever is at steady state, dx dt is 0, and the evolution here becomes flat. Okay, so hopefully you will agree that when x is equal to xss, dx dt equals 0, so that implies that we can find the steady state by solving for x in this simple equation, which I will do very quickly. So 0 equals alpha minus alpha x minus beta x. Factor out a negative x, so you have alpha minus x, alpha plus beta. And now add alpha, so xss equals alpha over alpha plus beta. Okay, so this is the steady state value for x in this differential equation that we had at the beginning. And it's worth taking a second to reflect on what this equation is actually telling us, because if you look, you have alpha over alpha plus beta, which is essentially equal to this equation of the definition of x up here. So that's sort of interesting, and you can intuitively sort of figure out, well, if we're looking at the proportion of active proteins, it sort of makes sense that if alpha and beta are constant, the steady state amount, or steady state proportion of active protein should be equal to alpha over alpha plus beta. I don't know, to me at least, it sort of, if you look at this long enough, that sort of makes intuitive sense to me. Okay, so now I'm going to work a little more with this equation. So we know XSS is equal to alpha over alpha plus beta, and there's actually another way that we can appreciate this fact by looking at this equation. So I'm going to do essentially a similar manipulation. I'm going to say dx dt equals alpha over, or minus alpha x minus beta x, and again I'm going to factor out a negative x, so I have alpha plus beta. And I'm going to divide both sides by alpha over, or 1 over alpha plus beta. Alright, and now we have this same differential equation, but we now have it in this new form. And what is this new form telling us? Well, this here, you will see, is x steady state, which is a constant, because remember alpha and beta we are assuming to be constants themselves. And this term over here is another constant, and I'm going to call this tau x. And the reason I'm going to do that, this is actually referred to as the time constant, and I'll talk about what that means a little bit more in the next lecture. But for now, just sort of realize that the time constant is scaling multiplicatively the rate. So the time constant scales the rate, and the time constant scales the rate, but it doesn't affect the steady state value of x. And if you look at this equation long enough, you can basically appreciate that as t goes to infinity, x is going to approach this steady state value. And why is that the case? Well, as you have this difference between a constant term and x. So if this difference is positive, i.e. x greater than xss, then in this case dx dt would be negative, because x is greater than alpha over alpha plus beta. So dx dt is negative, which means that x will be going closer to xss. X is greater than xss, but x is decreasing, and therefore getting closer to xss. And conversely, if x is less than xss, then dx dt is greater than 0. So in this case, x would be, again, getting closer to the steady state value of x. And, you know, it sort of goes without saying that if x equals xss, then dx dt equals 0. So this hopefully will give you some intuition as to why x approaches a steady state constant value for this differential equation that we have been talking about, and why it doesn't, you know, approach positive or negative infinity or oscillate indefinitely. It just approaches xss, and how quickly it approaches xss is related to this term here, the time constant, which I will talk about more in the next upcoming videos. All right, thank you.